You know, you watch an AI coding agent process a prompt, it hums away for maybe 60 seconds, and then it just perfectly drops a 20-line fix into this sprawling repository across a dozen different files.
Yeah, it really feels like magic sometimes.
Right. It feels like you are watching a 10x senior developer just effortlessly navigate the matrix. You assume it intrinsically understands the whole architecture of the code base.
Sure, I mean, that is the illusion we all kind of buy into.
Exactly. But we have this brand new paper today, straight out of Nanyang Technological University in Singapore from April 2026. It is called Neurosymbolic Repo-level Code Localization, and it suggests that the AI is effectively just using a cheat sheet. Welcome to the deep dive, by the way. Our mission today is unpacking exactly how these agents are, well, cheating.
Yeah, it is relying on a very specific kind of crutch. Current state-of-the-art models, systems like SwearAnk, Agentless, LogicAgent, and COSOL, they have been absolutely dominating industry benchmarks like SW Bench Lite.
Right, posting these massive scores.
Exactly. But the researchers at NTU identified this fundamental flaw in how we actually measure their success. They call it the keyword shortcut.
Which, honestly, it makes sense when you look at how real-world GitHub issues are actually written. Like, a developer submitting a bug report doesn't just describe the abstract structural problem.
No, they almost never do. They paste in a whole crash trace.
Yeah, a trace that includes the exact file path, or they explicitly name the class or the function where the error threw. So the benchmark data is completely saturated with explicit naming hints.
So instead of the model performing complex structural reasoning to figure out where a bug lives, it relies on this superficial lexical matching. It takes the function name from the prompt and essentially performs an advanced semantic string match across the repository.
Okay, let's unpack this for a second. It's like we thought the AI was reading and comprehending a massive textbook, but it turns out it's just using CETL plus F to find the bolded vocabulary words.
That is a perfect analogy. It is a highly sophisticated GRIOL plus F. And, that works perfectly when you already have the name of the broken function.
But I'm guessing that is a problem for more advanced tasks.
It creates a massive bottleneck for true autonomous software engineering. I mean, if you ask an agent to implement a brand new feature from scratch or refactor a structural pattern where it doesn't know the specific naming conventions in advance, well, that lexical crutch is completely gone.
And the NTU researchers actually proved this, right? They stripped the cheat sheet away entirely to see what would happen.
Yeah, they built a diagnostic benchmark called KA Logic Query. That stands for Keyword Agnostic Logical Code Localization.
Keyword agnostic, so no names allowed at all.
Right. They removed every single explicit file or function name from the prompts. They forced the AI to navigate based solely on how the code is built and behaves.
Combining structural dimensions with, like, behavioral attributes, control flow, inheritance depth, that sort of thing.
Exactly. The paper provides a really great test case for this to show how it works. They took the Astropy repository and created a purely structural prompt.
Oh, I remember this example. What was the exact prompt again?
The task was literally find all functions where the function has more than 15 parameters and the function is not an init method.
Wow, okay. Highly specific.
Right, and in a properly functioning system, this specific query isolates one exact function called convolve_foft.
And when they ran the state-of-the-art baseline models through this keyword agnostic benchmark, the performance completely cratered.
It was a catastrophic drop.
Yeah.
At the function level, which is the finest granularity of localization, the baselines hit a 0% perfect location rate.
0%.
Zero. The models that looked like master engineers just moments before suddenly hit a brick wall.
Wait. I have to push back on the mechanics of that failure, though. We are talking about massive 100 billion parameter LLMs here.
Yeah, they are incredibly powerful.
Right. They can architect a neural network from scratch, or they can translate obscure programming languages. Why is a simple structural query like counting the parameters in a function impossible for them to execute?
Well, it is the collision of two specific vulnerabilities. The first is what the paper calls the lost in the middle phenomenon. And this is really exacerbated by the sheer scale of modern code bases.
Because usually an LLM uses those specific identifier keywords as an attention anchor, right?
Exactly. The keyword signals to the attention mechanism what bulk of the code it can safely just ignore.
So without that explicit anchor word, the context window just floods. The LLM is forced to ingest the entire repository's structural context all at once.
Precisely. And this triggers the second, much deeper vulnerability. LLMs are fundamentally probabilistic text generators. They predict the next most likely token.
Right, they aren't calculators.
Exactly. So when they are forced to analyze a deluge of structural dependencies without a keyword anchor, they cannot perform rigid mathematical deduction over 100,000 lines of code.
They just try to probabilistically guess a path through a huge hierarchical graph.
Yeah, and the attention mechanism loses the thread. They just aren't built for formal deterministic traversal.
Okay, so if predicting the next token fails for this, we obviously need hard rules. And that brings us to the solution proposed in the paper, which is this framework called LogicLoc.
Yes, LogicLoc. They define it as a neurosymbolic approach. It basically offloads the structural traversal away from the neural network and hands it over to a symbolic logic engine.
Neurosymbolic. So
Yeah.
combining the neural net with old school symbols and rules, it separates the intent from the execution.
That is exactly it. The LLM handles the semantic, natural language understanding, that is the intent, but the actual execution is handed over to Datalog.
Datalog being a declarative logic programming language, right?
Right.
Rooted in database theory.
Right. It operates on hard facts and absolute rules. It is entirely devoid of probabilistic guessing.
But to make that work, to use Datalog, LogicLoc has to map the territory first. Before the user even submits a query, the system runs an offline pass over the entire codebase to extract what they call program facts.
Yes, the program facts are crucial here.
I'm assuming this means they are using static analysis tools to, parse the abstract syntax trees and map out the call graphs before the LLM even wakes up?
That is exactly the mechanism. They parse the code and construct a highly structured relational schema. It populates tables of concrete, observable facts.
Give me an example of what those tables look like.
Sure, so you get a table for methods with IDs and names, a table for calls, linking caller IDs to call IDs, tables mapping inheritance, variable declarations, parameter counts, and so on.
So it cleanly separates the raw structural data of the repository from any AI logical inference.
Exactly.
Here's where it gets really interesting for you listening. It's like pairing a detective with a forensic accountant. The LLM is the detective, right? It listens to your natural language request, interprets what you want, but it doesn't try to look through the books itself.
No, it would get lost in the books.
Right. It just writes a formal request and hands it to the forensic accountant, the Datalog engine, who only deals in hard ledger numbers and absolute rules.
The LM's only job in this translation phase is to map the user's English to Datalog predicates. So going back to our example, if the user asks for a function with over 15 parameters, the LLM writes a Datalog rule.
Setting up the logic for the engine to run.
Yeah, the head of the rule is the target function ID, and the body contains predicates like function ID and parameter count ID count, where count is greater than 15. It takes that formal Datalog query and feeds it right into Souffle.
Souffle being the deterministic inference engine they use.
Right. Souffle is this highly optimized execution engine that actually compiles Datalog into parallel C++ code.
Oh, wow.
Yeah, so it can execute a logical traversal across millions of program facts almost instantaneously. It physically traverses that map of the repository with absolute mathematical certainty.
Okay, but wait. Introducing a strict C++ execution engine creates a totally new failure point, doesn't it?
How so?
Well, LLMs hallucinate syntax all the time. If the LLM generates a Datalog query with, I don't know, a slightly incorrect variable name or an unclosed parenthesis, a strict engine like Souffle isn't going to try to guess what the LLM meant. It's just going to crash.
It would, yes. But the researchers anticipated that exact bottleneck. They built a synthesized check-refine loop that forces the AI to debug its own logic before the final query is ever executed against the full repository.
Oh, that's smart. So teaching the AI to debug itself, it starts with a parser-gated validation workflow, right?
Yes, exactly. It runs the generated data log through a lightweight syntax checker first.
So if the LLM uses a reserved keyword as a variable, the parser catches it, blocks the execution, and sends an error trace directly back to the LLM saying, hey, syntax error on line 3, rewrite this.
Right. It provides immediate, localized feedback. But this system actually goes much deeper than just catching basic syntax errors. Because what happens when the syntax is mathematically perfect, the query executes successfully, but it returns an empty set.
0 results. Meaning the LLM wrote valid code, but the logic was simply too strict for the codebase.
Precisely. And this is where LogicLoc employs intermediate rule diagnosis via conservative mutation analysis.
Conservative mutation analysis. That sounds intense. What does that actually mean?
Well, rather than just returning an empty result to the user and giving up, LogicLoc intercepts the failure. It intentionally mutates the LLM's original query to run diagnostic probes. It really wants to figure out why the query yielded nothing.
How does a conservative mutation actually work under the hood? Like, what is it changing?
It systematically alters the constraints of the query. One method they use is a string relaxation mutation.
Okay.
So if the LLM's original query demanded an exact string match, say, name equals config, the system mutates the predicate to a substring match, like name contains config.
I see. Making it just a bit fuzzier.
All right. Another method is the drop single atom mutation. The system drops one logical constraint at a time. If the query looked for a function with more than 15 parameters and a specific inheritance depth, it drops the inheritance rule to see if the parameter rule alone yields a result.
Wow, that feedback loop completely changes the dynamic. It doesn't just say error and make the LLM blindly guess a totally new approach.
No, not at all.
LogicLoc acts almost like a compiler with highly descriptive warnings. It's effectively handing the LLM a magnifying glass and saying, look, your logic executed, but we found nothing. However, when we temporarily dropped your constraint about the inheritance depth, we suddenly found 5 matching functions. Revise your query accordingly.
Yes. It heavily reduces wasted iterations and token consumption, and it allows the framework to classify the failure state into 2 distinct categories. Fragile empty versus stable empty.
Okay, break those down for us.
The scenario you just described, where dropping a single atom suddenly surfaces code snippets, that is a fragile empty result.
Meaning the constraint was just slightly too strict.
Right. The LLM's logic was structurally sound but slightly overspecified. The diagnostic feedback gives the LLM the exact delta it needs to correct the query on the next iteration.
And a stable empty result would be the opposite then. The system runs every possible string relaxation, drops every atom one by one, and still returns absolutely 0 results.
Exactly. In a stable empty scenario, LogicLoc informs the LLM that it has poked and prodded the query from every conceivable angle, and the requested structural pattern genuinely does not exist anywhere in the extracted program facts.
So the LLM realizes it's chasing a ghost and just stops iterating.
Right. It knows to stop.
That perfectly explains the massive disparity in computational efficiency highlighted in the results. I want to share these hard numbers because they are wild. LogicLoc achieved a 48.44% perfect location rate at the file level on the keyword agnostic benchmark,
Which is huge.
compared to the baseline's 0%. But more impressively, it averaged just 39.3 seconds and 16.2 thousand tokens to complete a localization task.
Yeah, and you really have to contrast that with LogAgent, which was one of the top-performing baseline models. To attempt the exact same task without keyword hints, LogAgent consumed an average of 393,000 tokens per task.
393,000 tokens for a single query. That is insane. And that happens because models like LogAgent rely on React loops, right? Reasoning and acting loops.
Yes, multi-round conversational loops.
The agent realizes it lacks a keyword, so it writes a Python script to search the repository. It runs the script, gets an enormous traceback error, tries to read the traceback, hits its context window limit, summarizes its own memory to save space, forgets its original objective, and then writes another search script.
It just spirals. It is burning compute tokens while blindly grepping a gigantic code base.
But LogicLoc completely bypasses that conversational spiral.
Exactly. By offloading the deep inference to the Souffle engine, the LLM only uses tokens to translate the intent and process the mutation feedback. It defines an entirely new efficiency frontier for autonomous agents.
Which obviously translates to enormous cost savings for enterprise teams running these models at scale. But efficiency aside, I think the most telling metric in the entire paper is the KA logic query neg test, the refusal metric.
Oh, absolutely. This is the most crucial test in the paper. The researchers intentionally prompted the models to locate code structures that explicitly did not exist in the repository.
They wanted to test the model's self-awareness because current AI tools generally default to a top-end ranking strategy, don't they?
Yes, they are designed to always provide a list of the top 5 or 10 most likely candidates, regardless of whether any of those candidates actually satisfy the user's constraints. They suffer from an inherent compulsion to guess.
Now, I have to challenge this a bit. From a human developer's perspective, I can actually understand why the models were tuned that way. Like, wouldn't you want the AI to at least give you its best guess, just in case?
In some contexts, yes.
Right. If I'm using a linter or a search tool in my IDE, fuzzy matching is great. I want the tool to take a guess at what I mean, even if I misspell a variable, so I can manually look at the list and pick the right one.
Well, that is true when there is a human in the loop to verify the output. But in the context of autonomous software engineering pipelines, a confident but incorrect guess is catastrophic.
Because there's no human checking it.
Exactly.
Yeah.
If an autonomous localization agent hallucinates a file path and passes that false positive down the pipeline to a separate coding agent, that downstream agent will start blindly modifying the wrong code. You aren't just wasting compute, you are actively injecting regression bugs into a stable build.
Oh, wow. Yeah. The agent acts on a hallucination and suddenly a completely unrelated microservice goes down simply because the AI felt obligated to return a result.
Right. Robust autonomous localization requires the discipline to explicitly avoid false positives. Because LogicLoc is grounded in the mathematical certainty of the souffle engine, it knows definitively whether the logical constraints were met. It doesn't have to guess.
So what happened in the test?
In the KA logic query neg test, LogicLoc successfully abstained and returned a no-match found response over 70% of the time. It had the deterministic proof required to refuse a bad prompt.
It had the self-awareness to confidently say, I didn't find anything. This research really forces a profound shift in how we evaluate the intelligence of coding agents. We have spent the last few years assuming that just scaling up the parameters and feeding a model more data would naturally lead to better architectural comprehension.
But that is a flawed assumption.
Right. True structural reasoning isn't about throwing a massive probabilistic text generator at a dense repository and hoping the attention mechanism holds. It is about understanding the boundaries of the neural network. It's using the LLM for what it excels at: semantic intent translation and orchestrating deterministic, rule-based engines to handle the heavy lifting.
And that framework points to a fascinating and maybe a little provocative implication for the future of software development as a whole.
Oh, what's that?
Well, think about it to mull this over. We've spent the last few years obsessed with making neural networks bigger so they can guess better. But if the next generation of AI coding agents is going to rely on extracting program facts into relational Datalog tables to understand our systems, our current programming languages might actually become the bottleneck.
Wait, really? Python and C++ becoming bottlenecks?
Yes, because we write in languages like Python or C++ because they balance machine execution with human readability. But if autonomous agents are doing all the heavy lifting, the future might not be about teaching AI to parse our legacy syntax. What if the true path to artificial general intelligence isn't relying entirely on the neural network, but teaching it to wield old-school logic engines?
So the future could be a return to symbolic programming.
Exactly. The future might be software engineers designing entirely new, Datalog-friendly programming languages. Languages optimized specifically for deterministic database traversal and neurosymbolic extraction rather than for human eyes.
Wow. We'd be writing code that is natively designed to be compiled into relational facts, building an environment where the AI doesn't have to translate our syntax at all. That completely inverts the relationship between the developer and the tool.
It really does. It changes everything.
Thank you so much for joining us on this deep dive. To everyone listening, the next time an AI assistant effortlessly refactors a function for you, take a second to consider the architecture underneath. It might be navigating the matrix, or it might just be exploiting a keyword shortcut. Keep questioning the tools you use every day.